Hey, what's going on, folks? It's Mike here, and welcome to the next lesson in our modern C++ series. In today's lesson, we're going to continue looking through the standard template library, and specifically in the algorithms portion. Now, today we're going to be looking at partitioning algorithms, which are fundamental to many computer science algorithms. Many of you might have learned quicksort, for instance, which uses a pivot and a way to partition two collections of data. So with that said, we'll go ahead and look at the standard template library, some of the operations that can help facilitate this. There's an example in C++ reference you can also see, but let's go ahead and start with the foundations and look at partition. So onwards to CPP reference, our favorite website here, and I'm going to go ahead to the algorithms library. And we've covered a lot at this point in this series, so you might want to wind back and watch some of the previous videos on this playlist if you haven't already. But we've looked at most or many of the non-modifying sequence operations. We've looked at many of the modifying sequence operations, and now we're going to go ahead down here to our partitioning operations. And specifically today, I want to look at is partitioned, which will tell us if we have a partition, and partition itself here. So let's go ahead and just start with is partitioned, and then we'll look at partitioned next here. So here's the fundamental idea with is partitioned. I'm going to go ahead and just draw a set of numbers here. And I'll draw them or represent them as a vector here. It doesn't really matter. And I'll have 1, 3, 5, and 7. So what I might want to do with this particular set of numbers to check if they are in fact partitioned is come up with some sort of predicate, right? How could I, for instance, divide or find a dividing point in this list here such that some condition is true? So let's go ahead and just pick the middle. That's often how we might think of our partitions, right? If we're sort of dividing things into even-sized teams or collections, however you want to think about it. And we could say if I have this as sort of the dividing line here, and I'm going to go ahead and put the predicate here, predicate, and then we want to specify some sort of condition for each of these elements here. And that's what the unary predicate's for here, which we'll see in the is partition and many of the partitioning algorithms. And I'm just going to go ahead and say something like our elements are less than 4. Okay, so that's the idea here with this sort of predicate, where everything that's less than 4 is to the left, and anything that doesn't satisfy that is to the right. Right? This is a way that you can sort of, again, subdivide this collection here. So where wouldn't this be true? Well, what if I had a collection like the following here? If I had, for instance, 1, 7, 5, 3, and can I find anywhere here where there's a partition from the left side, wherever that might be, some sort of range here, on the right side, where the elements are less than 4. So if I draw here, well, that's true, but we've also got something here less than 4 as well. And if I partition here, well, this isn't true, and this isn't true as well. And if I look here again, this is less than 4, but we don't have elements here or consensus that some of these are less than 4. So it's not partitioned here. Okay, so that's the basic idea with partitioning or dividing some data. So let's go ahead and look at the standard template library function here. And again, since C++ 11, this has been available, and until 20. And the reason it's until 20 is because we get the const expr version of these standard library functions here. And this is simply going to return us a true or false if we have a partition between a starting iterator, the end of our range we want to look, and then whatever our predicate is. Okay, so that's the idea. Now, we haven't talked about execution policies and some of these other ones, so we'll get to that, I think, once we finish most of the STL library, so we can go ahead and look at them. There's some different policies we can take a look at. Okay, now let's go ahead and see the complexity. And it says, okay, at most, well, whatever the range we're looking at in applying the predicate. So again, I've got to come up with hopefully some sort of simple predicate, something like less than 4 that can be checked in constant time. That's sort of ideal, but linear time, because I've got to look at every element and make sure sort of the left side satisfies this versus the right side. Okay. And that's sort of the possible implementation if we look at this for is partitioned, right? We're looking through the first set here until we break that predicate, right? Because we want everything up until some point to satisfy the particular predicate. And then so long as everything on the other side of our pivot, which is something that we use when talking about partitioning, satisfies things, then we return true. But if we ever satisfy the the predicate or the true condition again, right, which is what we are hoping to have just in our first half here. Again, let's go ahead and bring up this example here, right? So I just want to be able to look through the first half in this particular example, and then I look through the second half here, and as long as I don't break the predicate, like is true in this first case, then we are good to go, right? We just return true. So that's a nice sort of implementation here. Now let's go ahead and look at a few examples here. Let's just go ahead and set something up here. I'll go ahead and keep this off to the side here. Let's go ahead and just write a tiny example. And we're going to need, I'm going to use vector for this. We'll need IOStream just so we can see what's going on here. And of course, the algorithm library, which we're using here. Okay, and let's go ahead and just set up a data structure. Let's go ahead and use the one that we had before, V. And let's go ahead and say 1, 3, 5, 7. Do a few examples here. And let's go ahead and create V1 and V2. I'm going to let the compiler infer the type for us, so I'm not going to specify the template parameter just to make this as brief as possible, but you could put int or long or whatever you think the data type should be. Let's try 1753 here. Okay. And let's just go ahead and see if we set up a predicate or sort of the partitioning. So again, predicate's just a fancy word for the test that we want to be satisfied. And we're going to write this as a lambda function. Again, sort of emulating here. Don't need to capture anything. Take in one argument here. And we're simply going to return I less than 4. Okay, like our example that we did here. And let's go ahead and make sure this much compiles so far. Here's our main using C++20 and good to go. Okay, so let's go ahead now and check. And I'll just go ahead and say V1 test here. And we'll go ahead and call partition. So I need the beginning, V1 begin. And we could go ahead and make this a little bit bigger here. V1 end. And then our predicate that we want to test here. Okay, and the same thing for V2. And again, I want to look through the whole collection to see if it fails at any point here, or we don't have that pivot point here. And I'm going to steal something from CPP reference here. This here. Haven't really talked about cout too much other than using it, but there's a nice way, right? This is basically a global way to output here. But let's go ahead and have this just so it outputs true or false here. That's a nice little way to make things a little bit cleaner here. So I'm going to set the format here. And I want to, when I write out a Boolean value, write out true or false, not just 1 or 0. Okay. So let's just go ahead and write out our V1 test. And I'll put an end line here. And our V2 test here. Okay. So here is our program. Let's go ahead and give that a save. Give it a compile. Whoops, let's see. What did I do here? Maybe one little mistake. And you probably caught this. I just typed out partition instead of is partition. Hold on, we'll get to partitioning in a moment here. Let's go ahead and just fix that up here. Give you the full screen so you can see things. And, whoops, let's see here. Is partitioned. Yes, with the proper grammar here. There we are. I think that should do the trick. There we go. And if I run this, true and false. Okay. So again, we could see that if I'm looking at this, the first half does satisfy the predicate, and then the second half fails, which is what we want. Here, there's no clear like first half here. Okay, satisfies, or I should say, when I'm walking through this, this is less than 4. That's good. Let me find something immediately that's not greater than 4, or less than 4. Excuse me. That's fine. We want something that's greater. But then this value and this value, both of those fail the test. And as soon as we have one of them fail, it's not partitioned here. Okay, so that's the idea with is partition. So nice little test here that we can do here. Now, why might you actually use this and why I'm starting with this, right? You might actually want to do a pass in, say, linear time through your data before you would go through the effort of doing an n log n quicksort or something, right? Or if you're maintaining some sort of data structure, again, where you have maybe a min and a max, or sort of a double-ended stack or something that's partitioned in some interesting way, or double-ended queue. You could have a double-ended stack. Again, just it kind of depends on what you want to do with it. Again, this could be a useful function for that. All right. So with that said, let's go ahead and take a look at partition here. Now that we know about checking if something is partition and sort of have an idea about it. Standard partition here. Okay, so this is actually going to do the reordering for us, okay? And again, I'm going to ignore the one that's until 20 because we get the const expr version in C++ 20 here. And again, this is going to look pretty similar here. I'm going to take in the first and the last, so the iterator or our range that we want to create here, and then a predicate. And this is actually going to do the swaps by looking through our range and deciding, hey, are you less than whatever the predicate is? So if I look at this example, for instance, what it's going to do is look at this and say, well, do I need to move this anywhere? This is less than 4, so this is good. This isn't less than 4, so I need to move it somewhere, and sort of create a little like pivot here, okay? So then we'll kind of look at this element and say, well, this isn't less than 4. This is fine. Okay, this one's not less than 4, or excuse me, is. So we want to move it over to this side, okay? And effectively what we do here is we, let's go ahead and just, I would sort of put a bar here, and then I want to swap these two elements, right? Because all I care about is getting on the left side here, stuff that is less than 4, and on the right side, stuff that is greater than or equal to 4 here. Okay, that's the idea here for this particular predicate and how it might work. Again, this is a great review. Maybe some of you have seen this on quicksort or studied some other algorithms here, but how we can use this. Okay, so let's go ahead and take a look at this. And we can see a possible implementation here. Just looking at this, we have iter swap here, which I don't think we've looked at, but swaps the values of elements that given iterators are pointing to. Okay, so kind of interesting to look at the implementation here. We're looking at the first, and interesting, we've got a first, also a first look at this. We looked at find if in this series. Not sure if I showed you find if not, but looking through the range here and finding the first thing that doesn't satisfy some condition here of our predicate. And then returning in sort of the instance, well, if the first thing is equal to last, then just returning the first thing. But here's sort of the interesting part of the algorithm here, just kind of walking through one step at a time here. So we've got next here, which I think we might have looked at, another way to just kind of move through the elements here. Also, we want to make sure that, well, when we reach the end, we terminate. So move one element at a time here. And this is after finding our first thing up here that doesn't satisfy this predicate here. And then we check the value, and then we just swap them, and then we move again that sort of pivot point. Okay, so as I illustrated here with this little bar here. So again, if I had an element like 2 here at the end, then I would sort of move my pivot here, and then I'd swap 5 and 2. Okay, so that's the idea here. For how this works here. Now let's actually see here, in this particular case, I should get, let's get rid of this, 1, 3, 5, and 7, if I run partition on this particular data here, okay? Alrighty, so let's go ahead and take a look at the partition here. Now there's some interesting stuff going on here. Okay, we're getting in the iterator that's returned. Again, let's look at our return value. Iterator to the first element of the second group, okay? So interestingly, I guess just printing this out. Well, let's go ahead and just run partition on it, actually, just as a sort of example here. And then let's go ahead and see, you know, does this actually modify our data structure? Because if we look at this, okay, it's in partitioning operations. It's not in one of these categories. Is it modifying or is it non-modifying? Okay, well, we don't see it there. It's in its own category here. So that's not as clear. So let's go ahead and run it. Let's see what happens here. So what I'm going to go ahead and do here is, let's go ahead and I might want to hold on to that iterator here. So auto, I'm going to call this IT2. We know V1 is partitioned already, right? We ran that in our previous test. So I'm just going to run this on vector 2 here, which we know is not partitioned. And I want to say partition. v2 begin, v2 end, the whole thing. Same predicate, probably important to, if I'm checking if something's partitioned and I'm going to partition it, right, make sure you use the predicate. Kind of nice to write it in a function this way and sort of hold on to it. But again, just a little tip here. And then let's actually just write out the data structure here, meaning v2 here. So auto element, and again, these are just integers, so we can just use auto here. v2, let's see if it modified it, and we'll go ahead and write out each element here, and maybe a space between them. That's fine. And an end line. And they were doing nice stuff by copying and writing it out here. But let's go ahead and rebuild this, see if we did anything silly here. See if I spelled partition correctly. Did not. What have I done here? Let's see. This is a classic when I'm switching between too many programming languages. Colon. Compile. And where do I have that end line here? Oh, there we go. Just to make our formatting a little bit nicer. There we go. Okay, so let's go ahead and run this. Let's see what happened. And I get true, false, 1, 3, 4, and 7. Oops, I guess I had I should make that 5 to match our example. Let's see. You folks were screaming at me the whole time, probably. But there we go. Okay, so it is, well, let's do our test again here. So print out here. Let's see if we satisfy things. I've got to rerun is partitioned or the v2 test here. Don't need to recreate the variable. And let's go ahead and see. And that'll tell us, did it modify this in place? And in fact, it did here. Okay, for v2. And I'm just double checking carefully. v2, v2. Okay, so partition, pretty nice here. I mean, pretty clean algorithm here for how it works, or hopefully we sort of understand. And this is really one of the nice things about the standard template library, right? When I'm just looking at this partition here and sort of thinking about, well, when you're learning algorithms, whatever level you're at here, this is a fundamental building block to implementing things like quicksort here. And you can actually see as an implementation up here how quicksort's implemented, but I challenge you to see, you know enough at this point in the series to implement quicksort with the standard template library. I think it'd also be interesting to go ahead and implement quicksort without the standard template library. See which one you like better, right? You're gonna probably have to write this partition function, which is gonna look something like this otherwise somewhere in your code, but it is nice just to have partition, right? And this is, this seems pretty efficient to me. It'll work nicely with the containers and so on. So there you go. Alrighty, folks. So with that said, hopefully you enjoyed this lesson. You can find this lesson and more here on my website here at courses.msha.io, here specifically the C++ lesson. And let me know if you've had other use cases, other algorithms where this has been useful. And I'll be curious to hear your feedback as far as how you found writing that quicksort algorithm now that you know about is partition and partition. All right, folks, as always, thank you for your time and attention, and I'll look forward to seeing you in the next video.